introduce Jerome Gilles, who's a professor in the math department and a member of the Computational Science Research Center. And he's been working heavily, in different aspects of image processing, convolution, wavelets, actually, and let's see, this is the convolution that he's going to talk about today. How does it play into the array of things that he's been working on. Jerome, it's all yours.
Okay, thank you, Jose. So yeah, as Jose said, I'm an image signal processing guy. And in particular, it turns out that image processing for restoring images for atmospheric turbulence is actually one of the oldest topics I'm working on. I'm basically working on this topic since almost 15 years now. I started to work on that topic when I was working for the French Ministry of Defense, so way back in France. And I continued when I arrived at UCLA, and I'm still working on this topic. Actually, I am funded by the Air Force Office of the Scientific Research for this work on atmospheric turbulence mitigation, basically. Today's talk is a very particular aspect in that problem, which is the deconvolution aspects. And first, let me give you some idea, a general overview of what is the problem. So what do we have? We imagine we have a sensor, right? So a camera, basically, that looks at some objects. So here it's just a factice panel board, right? But it could be any target, like a tank or whatever. But here, the important point is that the distance between the camera and the object we are looking at is pretty far, right? And of course, in such long distance, almost every time we have the impact of the atmospheric turbulence. We all experience that, especially here in California, and given the temperature these days, right, it's very easy to experience that. If you are on the road, you look very far away, right, you can see that the image is dancing. Actually, we call it the image dancing, right? And so the problem is, if the camera, imagine we acquire a sequence of frames that I will denote Fi, right? How can we reconstruct hopefully nice, clean picture of the target we are looking at, right? And let me just show you two sequences. So I will switch my screen for a moment to another share. Here. So two sequences that were acquired in New Mexico, actually, in 2005. So this one is, so it's basically the board that I illustrated in my slide. So, and this one is also a board where we have different letters here. So the big one, it's not too complicated to imagine what they are, right? But as soon as you have smaller and smaller letters, it becomes way more challenging. Now, for this specific sequence, let me pause that for a second. For this specific sequence, this one was acquired with a very fast camera. So basically, it was, if my memory is correct, it was 1,200 images per second. So that's why we have this feeling of very slow motion in the turbulence, right? But of course, this camera was more for experimental purposes. And cameras that are embedded on systems, on military systems, they do not have such fast camera because they cost too much money. So we can't expect to have, I'm saying that because when we have this slow motion aspect, we might say, well, there is some sort of smoothness in the movement that eventually we can exploit. But it turns out that in practice for the cameras that are embedded in the system, it's not the case. So we cannot use that assumption. Okay, let me go back to my slides. Here we are. Oh, I took the wrong one, sorry. Here we go. Okay, so the question is, what kind of impact can we see on those images? So here it's just two frame that I randomly pick up within the sequence, right? So how can we model the impact of the atmospheric turbulence? So of course, I don't know if among our participants, we have people who do some fluid mechanics and this kind of thing, but you might say, there's a huge theory about turbulence from the fluid mechanics community, right? So why can't you just use that? Well, it turns out that in some sense, we will use it, but we cannot directly use those equations because for a very simple reason is they are way more too complicated to be embedded inside an image processing process. That makes the process way too complicated and way too computationally expensive. And today we have other type of algorithm that works as well as what we could do with sorry, someone is not muted. Okay, here we go. Yeah, today we don't need those equations. But as you will see in a second, in a few minutes, such of physics is hidden inside what I'm using. Okay, so let's go first to a very basic modeling of the impact of the turbulence on the images. In a very, one of the first papers looking at image processing for this type of problem was a paper from David Franks, where he suggested the following model, that each frame fi, right? So x is the position in the image, so that's the pixel location. So each frame is, so u of x is the original target, so the nice clean picture that we want to get back, right? And h is a blur. So first, we assume that there is a blur operator that applies on the clean picture, and the phi, that's a geometric distortion operator. So meaning that it will warp, locally it will warp, doing some random warps, right? To make those geometric distortion within the sequence, right? And we take the assumption that the blur is basically constant. I mean, it's not the same time scale as for the geometric distortion. So the geometric distortion move, they change very quickly, while the blur remains constant for a long period of time. Of course, across a whole day, H will also change itself, right? I mean, we have measurement that shows that indeed, if you compare, for example, between sunrise and sunset, that's where the turbulence is the most important. In that case, of course, you will not have the same type of blur as in the middle of the day, where the turbulence is a bit lower, right? But for a time scale of a few seconds or a few minutes, we can consider that H is constant, right? And only the phi depends on I. So I will represent the time in my case, right? It will be the index for time. So the question is now, how can we create algorithm that will be able to retrieve u of x from the images that we acquire, so the fi. Okay, so that's basically the problem. So how can we do that? Well, the idea from a mathematical perspective is, I would say, pretty straightforward. We just want to inverse those operators h and phi, right? And reversing the phi's, that's what we call a stabilization step. Stabilization because it just tries to stop the geometric distortion, okay? But it does not remove the blur. It just basically regularizes the geometry within the image. The second step, reversing H, that is the deblurring, which is basically a deconvolution process. And in this talk, I will focus on this second step, okay? But just for give you an idea how we can also do the stabilization, I just have this very short.
Excuse me, Jerome.
Yes.
When you say inverse, you're not talking about inverting H, the inverse.
Well, we will write, I mean, we cannot have a formal expression of the inverse operator. That's not possible because we actually don't know exactly what is the operator. But we will write it as an inverse problem.
Okay.
And then we will solve that inverse problem. Right? So it's basically doing computationally inversion of the operator.
Yeah, I got it.
So for the stabilization, there's an algorithm that we proposed quite a few years ago now. And if you look at the literature, most algorithms that do stabilization, they follow the same type of idea. It's just modifying a few things here and there. But the idea for the stabilization, so here I'm just talking about stabilization only, okay? No deblurring. So which means that my y here in this equation will be the HU, right? So it will be the blurred image, okay? So here, when I minimize respect to y, it means that what I want to retrieve is the blurred image, but with the geometric distortion removed, okay? So that's the idea. So the way we do that, well, as I just mentioned, we just write that as an inverse problem. So saying that we have some regularization term, J of y, right? And we want to minimize that regularization term with respect to y and the different phi's. Of course, under the constraint that we want that fi is equal to phi applied to y, plus eventually some noise, right? This type of problem can be recasted in this form, right? So we have this kind of functional that we want to minimize with respect to y and the phi, because of course we don't know the phi's, right? We don't know the mappings that do the warping of the geometry, right? So the question is, how do we actually estimate those warpings? And there is a pretty straightforward way to do that. So the idea is the following one. So let's take a look at this picture here. So imagine we have all those frames in our sequence, so F1, F2 up to Fn, right? Imagine we have, I mean, the stabilized or the blurry frame, the blurry image is, if you apply each phi, so phi1 will give you F1, phi2 will give you F2, and so on, right? So one way we can, imagine we know that, and I'll tell you in a second how we do it in practice. But imagine we have a guess for y, then a very straightforward way of estimating the warping deformation field is basically using an optical flow algorithm. That's the most easiest way to do it. It's not the only one. There exists also some other warping operators like based on diffeomorphism. So there is the Demons algorithm that exists that can also estimate such type of flow. But those algorithms are way more computationally expensive, and they have some assumption which works well if you have a very fast camera, but when you don't have this kind of regularity within the flows, they start to do not perform as expected. So actually the optical flow is basically the best thing to do right now. So of course you might say, well, yeah, but the only thing I know is the FIs at the beginning. I don't even know what is y. So we need an initialization for this y. And the very easiest way to do that is just taking a temporal average of all those frames. So that gives you a first estimate of this blurry image y. From that one, then now you estimate all the phi's, right? And the nice thing is those phi is just a vector field, so a deformation field. And so the inverse of those phi's is just doing the inverse deformation, right? And so then we can apply the inverse of each phi to each frame. Because of our regularization term here, then we will get an update of this y. And then we can iterate the process. From this updated y, you update the phi's, and those updated phi's will permit you to get an updated y, right? So we have an iterative process, which actually converges pretty fast. In practice, usually between 10 and 20 iterations is well sufficient to get a stabilized image. So to illustrate what we get from such stabilization, based on the two sequences I showed you before, this is what we get. So the left column, that's the initial frame. So those frames that I extracted randomly from the sequence for each sequence. And on the right, you have those stabilized frames, right? So you see that compared to here, for example, you see that the bars is completely distorted here, right? While here, it's pretty straight, right? So the algorithm compensates those geometric distortion in a pretty nice way. You can also notice that, for example, in this frame, there are some dots on the top here. that we actually cannot see them, right? Because they are completely warped in some very weird ways. But the stabilization push them back on the image, so we can see those dots, right? Now, of course, this is, as I said, this is a blurry image, right? And I mean, we can see it because we don't have, I mean, I think you guessed that this board was basically painted black and white, right? There were no grayscale on this board. It's just white and black. So ideally, what we want to find is to have way more straight edges on each object, right? And in particular, when you go to the high spatial frequencies, so towards that way, where the bars become thinner and thinner, we expect to see better separations between the different bars by removing the blur, right? So the question is now, how do we perform the deblurring aspects? And of course, the blurring process is a convolution process. So the most natural way to do a deblurring is by using deconvolution. But the problem is there's two ways of doing deconvolution. That's what we call the non-blind and the blind case. The non-blind case is basically, you know what was the blurring kernel, right? And based on that knowledge, then you just run some, again, inverse problem, which uses that knowledge and you get your deblur image. The blind case is when you have no idea, well, you don't know what is the blurring kernel. And that means that you also need to estimate the blur kernel. And the blind case is, of course, way more complicated in most cases. Right? And of course, for the turbulence, we don't know, I mean, at time t, we don't know what was the kernel, right? So we have to estimate that kernel. Now, it's not, I mean, I called it a blind algorithm, but actually we have some knowledge. And that's where that knowledge actually comes from the physics. And that knowledge is from some very old paper. Actually, the original paper is from David Fried. That was at the end of the 60s. So David Fried was working in optics and especially the impact of turbulence on optics. And he has this very nice but very complicated paper where he mixed the optical theory with the Kolmogorov turbulence theory. So he was able to mix that together. And the interesting part is that he showed that we can actually design, I mean, we can find a model for the blurring kernel corresponding to the turbulence as the impact on images. So this kernel, I denoted MF, so F as Fried, of course. This kernel is expressed in the Fourier domain, so that's why omega represents the frequencies, right? And the way the Fried kernel is designed is it's the product of two terms. The first one is M0 of omega and MSA of omega. So what are those two terms? The first one, M0 of omega, it's basically given by this, and it corresponds to the MTF. So MTF is modulation transfer function. That's basically the transfer function of, in that case, of your system, so the imaging system, your camera, and the different optics of your camera, plus the impact of the atmosphere, but where basically there's no turbulence, right? So like if you, I mean, that kind of kernel is also used when you are in very short range. You can use that kernel to model the impact of the optics of your system. So that's the first term, M0 of omega, so it's pretty straightforward. I forgot to mention that I normalize the frequencies between, I mean, less than 1. Now the second part, which is the one which is the most interesting for us, is the one that corresponds to the impact of the atmospheric turbulence. And for this one, basically there are 4 different parameters. The first one is D. D is the pupil diameter of your imaging system, right? L is the distance between your camera and the target. Lambda is the wavelength that your system is working, I mean, visible, infrared, whatever, right? and the Cn square. The Cn square is a physical parameter that reflects basically the level, the amount of turbulence in the atmosphere. So now, if you know those parameters, basically, you can compute some intermediate variables, so k, rho0, r0, capital P, capital Q, and capital X, right? So you see it's very straightforward equation from those 4 parameters. When you get those ones, now you can compute the quantity V of Qx, which is, the expression sounds a little bit weird, but it's actually pretty easy. It's just very, very basic algebra from those different quantities that we can compute before. And now that you have, at the end, when you have this capital X and you have this V of Qx, that's what appears in the formulation of the MSA of omega part, right? This part of the kernel. It's just the exponential of this coefficient, that frequency, that times that coefficient here, times omega square, right? And for those of you who are familiar with the Kolmogorov theory, you might say, oh, yeah, that looks familiar, right? The 5/3, the 7/3, those are the exponents that appear in the Kolmogorov turbulence theory, right? And so that's why we have those powers, those very specific powers here. It actually comes from the Kolmogorov turbulence theory. So, here it's just pretty basic algebra to build the kernel itself, assuming that, of course, you know those parameters, right? So if you know the parameters, then it's pretty easy to build, to have a formal expression of the free kernel, right? So now imagine that we have this free kernel, the way we can use it to perform deconvolution. So that's what we proposed a few years ago, is to use that free kernel within an inverse problem. Right? So Y is my input image, right? My blur image. MF is my free kernel. And what I want to retrieve is the image X, which will be the clean image, right? And here, D, at that time, we used a Framelet decomposition operator. So we were, the regularization term was just using a sparsity within the Framelet domain and of the transform of X, right? And the nice thing with the Framelet is that it forms a tight frame, and that makes that DD transpose is equal to the identity. That is very useful when you derive when you want to minimize this equation with respect to X, right? So numerically speaking, we use the split Bregman iteration at that time, where the intermediate variable D was the capital D times X, so the Framelet decomposition of the image X. And then we have 3 different steps in the iterations. The first one is we update the image X itself by solving that problem, which is an L2 problem. So that is very straightforward to minimize. You can choose a basic gradient descent, or you can also directly solve it inside the Fourier domain, which is actually what we did because the kernel was defined in the Fourier domain. So it was very natural to directly work in the Fourier domain. Update the intermediate Bregman variable, so dk. This one, if you look carefully, the one norm of D corresponds to this part here, right? And there is an extra term just to make sure that that small d is equal to dx, right? So that's the purpose of that term. And now it's an L1, L2 problem, and the solution of such problem is also very straightforward. It just basically corresponds to do a soft thresholding of the coefficient of the Framelet coefficient. So basically, you take the Framelet transform, you threshold those coefficients, and you do the inverse Framelet transform, and done. And that's it. That's the only thing to do. So it's also very easy to do, numerically speaking. And the last one, which is that's something which is very specific to the split Bregman method. That's just typical algebra, so that's very easy to compute. So that algorithm is very straightforward to implement. It just takes a few lines in MATLAB. If you are interested, I think it's available in my Bregman cookbook that you can find on my website. So yeah, it's solving this problem is very easy in practice. Now, of course, there are those 4 parameters. And at that time, the assumption we took, it was that, okay, D, so the diameter of your imaging system, and lambda, which is the wavelength at what your imaging system is working, those 2 ones, I mean, if you know the imaging system, it's pretty easy to know those 2 parameters, right? Capital L, which is the distance between you and the target, it's also pretty okay to assume that it's known, because usually when you have an imaging system, it's supposed to work for a certain range of distances, right? And eventually, even if it's not necessarily a good idea for military application, but you can also use a laser to measure the distance, right? So that could be an option too. So D, lambda, and L, it's not very bad to say that we are assuming that those parameters are known. Now the big problem is the CN square. Because the CN square parameter, so it is actually possible to measure it. The problem is the measurement requires some very specific equipment that needs a laser source and also a sensor at the other side. And you can very easily imagine that for military application, if you are looking at a target which is at a certain distance, you will not send someone just to put the sensor there and be able to measure the CN square, right? That's not possible in practice. So, which means that for a military application, measuring the CN square is not possible. Okay, so that's as easy as that. So how did we deal with that? What we did is we use the fact that we know that the CN square parameter is within a certain range. I actually forgot the exact numbers, but something like 10 to the negative 16 and 10 to the negative 12, right? So the smaller the parameter, the stronger the turbulence, basically, right? And so we know that the CN square value is within that range. So what we did in our previous paper is basically a brute force approach. We said, okay, well, we sample that interval, right? And we perform a deconvolution for each of those values, okay? And we found that calculating the total variation of the deblurred image was a good indicator of how good was the deconvolution. And so for each deconvolved image, we compute that total variation for them. And so that gives us some points on the curve, right, which represents how good was the deconvolution. And so, of course, we cannot compute too much of those points because that would be a burden in terms of computation. So we just computed a few ones. We got those TV points, the total variation points. And what we did is then we did an interpolation with the 5th order polynomial. We found that this is the one that was the most efficient. And when we got that interpolation, then we found what was the CN square that gives us the maximum of that curve. And that was our estimated CN square, which we used for a final deconvolution to build the final fluid kernel. It worked pretty well, actually. If you look at our previous paper, you will see that the results are pretty good. The problem is, of course, for each value of the CN square you want to try, you have to perform this algorithm for each value. And in terms of computation, that takes a lot of time, way too much. So, which basically means that, yes, it gives you good results, but it cannot be used on the battlefield because it's too slow. So we have to find something more efficient in order to perform the deconvolution. And that's what we did with the new algorithm, with the BATUD algorithm. The idea is the following one. Let me go back here for a second. If you look at the expression of this MSA, right? So the M0 of omega, I mean, this one is straightforward. We keep that one, right? As you will see later. What we are focusing on is the expression of this MSA. Now, if you look very carefully here, at the end of the day, in this expression, there are only 2 different parameters. You have this one, right? The negative 2.1x to the 5/3, and you have this v of qx. So the idea is, instead of trying to estimate the original parameters, and especially the sin square value, why not trying to estimate those coefficients here directly, right? So then our idea was, okay, let's reformulate that kernel in a different way, but equivalent way, of course, following this idea. So the kernel that we use is this one. So now MA of omega is A of omega exponential of a sum of weighted functions. Oh, okay, I didn't notice that. Fi here is not the initial frames, it's just a function of index I. It's nothing to do with the original frames. Sorry about that, I didn't catch that. So yeah, we write the kernel. It's a very general expression for basically an exponential kernel, right? Exponential type kernel. It's just the exponent in the exponential is just a linear sum of functions, right? So we assume that we have n term in that sum, right? Big A here in the front, that's a function from R plus to R plus, and those functions Fi again are from R plus to R, right? And we assume that they are fixed and known, right? Now, what is unknown is the set of parameters AI, right? So if we denote that in the vector form, we denote the vector A as the vector of the coefficient A1 up to AN, right? And the idea is that we will estimate those parameters. Okay, that's what we want to do. So just to illustrate that we actually get back the Freight kernel is that if you think that A of omega is my original M0 of omega, right? The part of the kernel which is without turbulence, right? N equals 2, so meaning that I have a sum of two terms here, where A1 will play the role of 2.1x to the 5/3, A2 will play the role of this quantity here, right? And if I choose the function F1 be the negative power to the 5/3, and the F2 function being just the square function, then you see that if you plug those things in this expression, you get back the expression of the Freight kernel, right? So except that in our case, we basically get rid of this, and we just use A1 and A2, and we want to estimate A1 and A2, right? Eventually, something that you might argue is, yeah, we will estimate those parameters independently of each other, while in practice, in the original Freight kernel, they are not independent, right? Because it's the same capital X, right, in those expressions. But it turns out that we actually get the same result at the end. As you will see, we get back almost the original kernel, even if we consider that they are independent. Just a quick note, this general expression can be used for other type of kernels. We didn't investigate those cases, but basically a Gaussian kernel will correspond to choose A of omega equals 1. The sum in here is just with only one term, where A1 will be gamma squared divided by 2, and the function F1 will be negative the square function, right? So this expression is very general. I can express many different exponential type kernels. So here we use it for to model the Freight kernel, but it can also be used for other type of kernels. So yeah, I don't know if you are interested in some deconvolution process that use some exponential type kernels. I mean, I'll be happy to help you and look at your problem and see how we can model that. And actually, the code that we have is very generic, so we can plug whatever function we want. So pretty easy. Okay, let me now move to the deconvolution algorithm itself. So the idea now is, again, I want to get back my clean image X, right? I need to estimate the parameters A, and there is an extra parameter lambda that I will explain in a second that we will also want to estimate. So our problem, our deconvolution algorithm is, again, nothing else than writing an inverse problem that way. So the first part, y minus ma times x. So here, those are matrix notations, right? So that means that this product here will correspond to my convolution. Okay. Here, so that y minus max, that's just the data fidelity term, right? And using the L2 norm just means that we consider it's a wide Gaussian additive noise of standard deviation sigma, right? And in practice, we can estimate that sigma. There exists several algorithms to do that. When you give an image, it estimates the sigma of the noise. So we use one of those algorithms to estimate the value of sigma. So that's the purpose of the first one, that's just the data fidelity term. The second term, R of x, that's my regularization term, in order to just make the problem well posed. And there are several options for that, and I will explain you in the next slide, the one we choose. The last term, no, the third term here, MA, so that's just basically the energy of the kernel. The idea is here is we don't want to have the kernel go crazy, right? So this one will help in the estimation of the parameters A, okay? So this one constrains the kernel to stay in a nice shape, I would say, okay? Now the point is, of course, when you write such problem, you put such lambda parameter, which is just a tuning parameter, right? And there's always the same question, how do you choose that tuning parameter? And experimentally, we observed that choosing small values of lambda was not a good idea. I mean, because we want to keep that small, right? And so the way you want to keep that small is if you allow very small value of lambda, then it means that you are also allowing very large value of the kernel. And we didn't want that. So we also wanted to keep, to penalize small values of lambda. And so that's why we added that term here, because if you have small values of lambda, then that term will become very large, right? Which goes against the fact that you want to minimize this expression, right? And this alpha square, that's now an extra parameter, but it turns out that we observe experimentally that you can't fix that parameter, and it basically always works for any images that you provide. You can use the same value of alpha. So basically, you can consider that alpha is basically known, and there's no need to change it. So at the end of the day, then now we can actually minimize this whole quantity with respect to both x, so the clean image, a, which are the parameters for the free kernel, and lambda, which is this regularization parameter here. So now about my regularization term R of x. So I don't know if some of you were there. Basically, I don't remember when was Charles' talk. He gave a talk at the CSRC Colloquium, I think something like about a year ago, where he showed some Gaussian mixture model to model natural patches in images. And that can be used to perform different types of inverse problems, denoising, deblurring, super resolution, and several other things. And so, and the point is that they developed a very fast algorithm to solve those type of minimization problem. And we decided to work with that type of algorithm because it basically gives state-of-the-art results in terms of deblurring and denoising. So the idea is that the penalization term is written that way, right? N is just a normal, so a Gaussian, right? Of this quantity, zero mean, and sigma is the variance, the covariance, right? And there are some weights here, and those weights are learned from a collection of 2 million patches that were coming from the Berkeley segmentation datasets, right? And that learn step was actually done in this paper, and it's available online, so you can just download the trained Gaussian mixture model. And so we just use that here. So in practice now, how do we solve the BATUD algorithm, numerically speaking? So we have an iterative algorithm which first updates x. So that means that the new x will correspond to minimize this quantity, okay? And so that can be easily done by using the algorithm that Charles and his collaborator have developed 1.5 years ago, about 2 years. So that's called the FEPLL algorithm. And actually, their code is available on the GitHub here at this address, if you are interested. So that's very easy to solve numerically. We have the code, right? For this one, updating lambda, it turns out that there is a closed form solution for that. So lambda t plus 1 is directly given by that. So very, very easy to compute and very fast, of course. And the last one, which is updating the parameters. So what we do is we recast this problem in this way. So if you look carefully, you have the 2 norm here that corresponds to this piece minus the y square, which we remove because it does not depend on a, and it's just a constant term, so it does not matter for the minimizing, so we remove that term. And this one here corresponds to this piece here. So then we denote that quantity E of A, right? And now the way you can give an update of those parameters A is by using a very basic Newton's descent approach. So it's just, okay, the new A's are the previous A's minus the inverse of the Hessian matrix times the dot vector of the derivatives of that quantity EA, right? And each of those terms are given by those quantities. They might look pretty complicated, but actually it's very easy to compute. It's again just basic algebra. And numerically speaking, all your integrals, they become to a sum. So it's just summing across all pixels. So it's very easy to implement. And in our case, for the free case, since we have only 2 parameters, A1 and 2, that matrix is just a 2 by 2 matrix. So it's a very small one. So there's only 4 parameters to compute. So pretty easy and pretty fast. So that's basically how we solve the model numerically speaking. So I don't know if there are any questions right now about the model itself. I don't know if you guys can unmute yourself.
No question from me, Jerome.
Okay. Okay, so let me continue and I'll take question at the end anyway. Let me show you some results now. So the first thing we did is by simulating the blur, because of course we have the expression, I mean, we have a formal expression for the blur, right? So we can just pick up parameters, build a free kernel, and then apply that free kernel on some images to create the blur, a simulated blur, right? And based on that, then now we can apply the algorithm to get the deblurred version, right? And so what we did also is to compare with what we call an oracle, which is basically a non-blind deconvolution where we use just the FEPLL algorithm, where we provided to that algorithm the kernel that we actually used to create the blur, right? So we wanted to compare the blind algorithm versus a non-blind algorithm, assuming that we use the kernel that was used for the simulation. So what do we see here is the left column, that's white. So that's the blurry image, right? And those different rows, they represent weak turbulence, so weak blur, medium blur, and strong blur, right? And you can see it on the images. The more you go downward, the less you can see the details in the fence, for example, right? And some textures are also disappearing here. The second column, that's what we get with the non-blind case. So we use FEPLL, providing that we give him the blur kernel that was used, right, for simulate the blur. And it gives us pretty nice results for each cases. So those numbers that you see here, those are the first number is the PSNR. So the larger that number, the better, right? And the second number is the SSIM. So the closer to 1, the better, right? And the last, I mean, the third column is using the blind case. So the algorithm which estimates the parameters of the blur itself. So it has no knowledge of what was the blur used, right, to simulate the blur. And you see that the images are also pretty good, right, on each cases. And the numbers, so of course, it's not as good as the oracle case, but it's pretty close. I mean, the numbers are pretty good, right? If you look at the PSNR, for example, and the SSIM, it turns out that eventually, even in that case, the SSIM is actually better than the Oracle case, right? And the last column that you see here, I mean the fourth one, that's on the top, the top half, that was the used kernel to create the blur, right? And the bottom part is that's the kernel that was estimated by using the blind algorithm, right? And you see that, so that number is just basically the relative error between the two kernels. The expression is on the next slide. So you see that those numbers are very small. So the estimated kernel is actually very close to the kernel that was used to create the blur, right? So that's pretty cool. Those graphs here, that's just the convergence rates by estimating each variable to see which one converges the fastest, and it turns out that the image itself converges very fast to its final solution. So that basically means that eventually you don't need to have the most optimized lambda and parameters A to already get a very nice deblurred image. So that's quite nice. To show you, so we perform those simulations on many different images on the whole data set, right? By simulating different type of blur with different parameters. And what we did is different type of noise also, so sigma 1, sigma 2, sigma 3. And here, so the different categories here, that's the PSNR, right? SSIM, and the key area, that's the relative error in the kernel. That's again the smallest that number, the better you estimate the kernel. And what you can see is, so the first line for each of those categories, that's the blur image, right? And then you have the BATUD algorithm and the Oracle one. So the Oracle one, yeah, I mean, in most cases, I think in all cases, my memory is correct. Yes, in all cases, the Oracle, of course, does a little bit better because it knows what was the used kernel, right? But the BATUD algorithm performs very well as well. I mean, it's not as good, but for many cases, and in particular for the strong blur, that's the most interesting part, is that the worst case, that's where our algorithm performs the best. Because you see that those numbers are actually pretty close to each other, right? For here. And of course, they are better than what was the blurry image. Okay, so we get back a nice image at the end. Let me show you two examples of what we get. Again, that's on simulated blur. Those two images, those are the blur images, right? And that's the one that we obtained with our algorithm. So, I mean, you can see that the textures are back, right? On the trees, the leaves, these kind of things, the fence. I mean, it's very blurry here. All those different things, I don't know what they are, by the way, but those different details here that were very, very blurry, I mean, we get them back, right? That's actually pretty cool. I don't know if you can see, but there's also some details here on the roof, I mean, under the roof, that we can see that I'm pretty sure nobody can guess it here, right? So that's pretty nice. And same thing on this one. So this one, I think the second one was a stronger turbulence case. But again, we get back a lot of details in the image. I mean, like look, for example, here in this area, here it's pretty complicated to see what were the details here. But here we can almost count how many parts there are in the fence, right? So it's pretty good, right? So that was for the simulation. Yeah, the next thing we did is, because if you look at the literature about the turbulence mitigation algorithm, you actually see that a lot of people, they use some standard blind deconvolution algorithm, the very specific ones and very general ones that do not assume a very specific model for the kernel. And so we decided to try our algorithm against the most well-known algorithm, and it's those different algorithms like CLS, COT, MLE, OBD, SG, and ZWZ. If you want to have an idea what are those algorithms and a very short description, I will refer you to the paper that we wrote. The details are there. But what is interesting is, so again, we have the PSNR and the SSIM. Unfortunately, we don't have the values for the kernel, the relative error for the kernel, because not all those codes, so all those algorithms, their code is available online. But unfortunately, not all codes return the kernel, the estimated kernel. So we are not able to compute the relative error in the kernel estimation. So that's why we just have the PSNR and SSIM. But you see that for both metrics, the BATUD algorithm, our algorithm, performs better than any other existing blind deconvolution algorithm. And those are, for most of them, they are the state of the art, basically. So that, and for some of them, I mean, we beat them by a lot. 7 points in the PSNR, that's actually a lot. So that's actually pretty good. And the other nice thing is that our algorithm is actually faster than any of those. So that's another advantage too. Just to show you also, several of those state-of-the-art algorithms, they have plenty of issues, especially when you start to deal with strong blur, this kind of thing. They start to create some artifacts. So here are just a few illustrations of artifacts that come from different of those blind deconvolution algorithms. That you see this one, for example. Sometimes it creates very strong ringing artifacts. So yeah, we get back some very sharp parts in the image, but at the same time, those artifacts are so big that the image becomes useless. This one, actually, I don't know why. Sometimes it creates those very bad type of noise. Sometimes it actually does not perform much deconvolution. So it basically means that it cannot estimate the kernel properly. So that also shows some advantage. Well, by the way, with our algorithm, we never observe any type of those artifacts in any of the images. So just to finish, let me show you a few results on real images. So here, again, on the left column, you have the blurry one. So this one, you already saw it. This one, that's actually an image that we took on the football field at SDSU. So we have a couple of sequences that we took there. And so that's a stabilized image, also with blur. And if you look carefully that on the deblurred image, we can better see the fence here, right? The details on the fence, the textures here are better. I will not say that we can read that, but it's definitely better than that. The edges on the bricks are also way sharper, right? Now for this image, those letters here, I mean, way easier to read, right? I don't know if you can read that one. I know this one is pretty tough to read, but, and I'm biased because I know what it is, but I think you can guess that this is an E, right? You might guess that this is an R, right? It's actually a bear. So it's way better, way easier to guess compared to that. I mean, even here, if you can guess that this is an E, you're pretty good, right? And so here, I just illustrate the corresponding kernel. So, and that shows that as expected, on that day, the turbulence was not very strong. So the kernel here is pretty large, right? And compared to this one, when the turbulence was way stronger, so the kernel is narrower compared to this one. And that's another example. So same sequence, but in a way worse day. So the turbulence was just crazy that day. It's basically impossible to read. At least the first two lines, basically impossible to read. Here you see back some letters, not all of them, but it's definitely sharper. And the kernel is even smaller, right? And this one is a sequence coming from the army. That was, I think, 1 kilometer distance on this one. And again, we have a lot of blur. Some details that are pretty hard to see here are way sharper here. I actually think it was a person there at this position. And that's, again, the estimated kernel. And so the image is sharper, cleaner, and easier to interpret. So let me conclude. So what we have proposed is a simplified version for the free kernel. But as I said, actually the model that we propose is more general than just dealing with the free kernel. So we can use it for different type of exponential type kernel. So I'm open if you have any problem dealing with that type of kernel. We can use the code pretty easy. The numeral algorithm is very, very straightforward, very easy to deal with. And it's actually 2 to 4 times faster than all the existing blind deconvolution algorithms that we tried, which also is a huge advantage to the state of the art. I already mentioned that you can use it for other type of kernels. And we are thinking of, we are pretty sure that it should be feasible to have a real-time implementation of that method. Because what takes most of the time is the FEPLL part. But from what Charles told me, they are convinced that it can be run in real time. It's just a matter of optimizing the code in a proper way. So if we have time, we don't know yet, we might try to implement that on one of those small, I have a NVIDIA Jetson Nano card with a GPU on it. So the idea is maybe at some point we may try to implement that algorithm to work real time on this kind of very small card. Right? If you are interested to learn more details, the preprint of our paper is available on Charles' website, and the code will be available there. It's not yet because we are waiting that the paper is definitively accepted. It's we submitted the revision 2 weeks ago, so it should be soon, I guess. The revision were pretty straightforward, so we are hoping to get a final acceptance soon. But the code, so it's a MATLAB code. It will be available on Charles' website as soon as the paper will be accepted. So, but the preprint is already available there, so you can download the preprint paper. That's it. So, any questions?
Jerome, Ricardo here. Can you hear me?
Yes.
So I have a question on your state-of-the-art very nice results. Mm-hmm. In the images that you captured, there are some specific features that are very well recognizable. For example, they could be letters, circles, lines, etc. Could you be able to somehow use some sort of artificial intelligence that recognizes a specific feature that is already kind of a fixed feature, like the A in one of your images, and use that to help you to reconstruct the rest of the image, because that part you're pretty sure that it's an A. So okay. Why don't you use the fact that you already recognize a bit of the image and you know exactly what it is?
I see what you mean. Okay. Let me be nice. No, the point is here, our goal is not to recognize a specific object, right? But it's to have a deconvolution algorithm that will retrieve the details and a better interpretation, get a better interpretation of the image, right? For the human, or eventually for an artificial system. Right, whatever. Now, you're right. If you know, if your application is really to recognize specific types of targets, right? That could be letters, that could be a specific type of vehicle, for example, right? That could eventually be some knowledge that you can incorporate in a specific algorithm. But it will be quite different. It's a different approach. It's a different philosophy. Our goal was not to recognize specific objects, right? Because for the here for the military applications, yeah, I mean there's different type of how they can use this type of algorithm, but for many of them actually they have no clue what they are looking at.
Yeah, but I'm not specifically asking to recognize parts of the image per se, but for example, if you have a line that you're sure that that line is a line, then, I mean, you're trying to reconstruct something that you already know what it is, that is a line. And if you know that that's a line, that will give you an idea of what the turbulence, what the convolutions has to be, because that thing has to recover a line because you extrapolate that that thing is a line.
Okay.
Forget about if you're reconstructing a car or a bomb or whatever, just a specific feature in a corner of the image that can help you.
Okay, I see, I see. So actually this, in some sense, it's already included there. And by that, I mean that inside the FEPLL algorithm, so because it's a patch, I mean the Gaussian mixture, right, that is used, let me go back here, right? So that Gaussian mixture, which actually contains about 200 Gaussian, if my memory is correct, this once, when you do the learning of those weights, the idea is that you basically you learn the distribution of different type of patches. And since those patches were extracted from those 2 million, I mean, those 2 million patches, right, were extracted from very generic images, what happened in practice, and that's basically also what happened in neural nets. It's that they really catch patches which have very nice features, and so basically patches which have lines, these kind of things, right? That's basically what is learned, right? So I would say you're right. This is kind of hidden inside this GMM model here.
Any other questions, comments, complaints?
Jerome.
Compliments?
Yes, Mark.
Hi. Yes, very nice.
Yeah.
Just a curiosity on, I think it was on slide 12, where you're showing the convergence graphs.
This one? Yeah.
Yeah. Just a curiosity there on the bottom lower right, there's a little blip. There's a little increase before. Yeah, just curious about it.
Yeah, that's, I mean, we don't have any clear explanation of why we have those bumps here, right? What we did in practice in the algorithm is that we put a stopping criteria such that when we arrive at such bump, well, we stop the algorithm, right? That's how we deal with in practice in the algorithm. But you're right. I mean, these small things, I mean, we don't have explanation why it does that. It's a bit strange.
But then you get past the bump and then it behaves nicely again.
Yeah, but the point is, again, the blue curve, which is the convergence of the image, the deconvolution image, right? You see that this one converges way faster.
Yeah.
I mean, from here, right, you already get basically the final image, right? So you actually don't need to go so far. Because if you see that the ticks here, that's 50 and 100 iterations, right, of the algorithm. But in practice, we do what, 20 iterations? No more than 20 iterations in the algorithm, because each time we see that between 5 and 20, the image itself has already converged. So in practice, I would say, I mean, here we did those plots just for a matter of showing what's going on, right? But in practice, we actually never go so far. And that's interesting, that the fact that the images converge so quickly, that's why it makes our algorithm pretty fast. Because we just need a couple of iterations in order to get the convergence. The FEPLL method is actually, I mean, very efficient in terms of deblurring. So, but it's a good catch. I mean, we don't have any explanation about why those things happen here.
Another quick question. Suppose you had a windy condition where there was a prevailing wind. Would you ever have asymmetric kernels or anything?
That's something we started to look at. Yeah.
Okay.
You're right. You in that case, your kernel, basically your kernel here will not be isotropic, but it might be anisotropic, right? It might be more an ellipse instead of just a disk thing, right? And that's something that, yes, we started to look at that. We didn't finish it yet. Hopefully we will someday. The point is actually, right now we don't have any sequences that show those type of things. But I mean, it exists because I was able to observe it when I was in New Mexico in 2005. with the NATO group when we did those acquisitions for some of those images. And that's something that at some time of the day when sometimes, yeah, the wind shows up for just a few seconds, and you can see the atmosphere that's moving on the imaging system. It's pretty incredible to see. So yeah, it can happen. Yeah, it can happen. And so that could be something to look at. And another thing that we are also thinking of is that, and that's an idea that was used in other papers about turbulence mitigation, is that there's actually no reason that the same kernel is the same everywhere on the image, right? And especially when you do ground-to-ground observations, when you do the measurement, for example, the measurement of the sin square. So again, in New Mexico, my colleagues there, they had those equipments to do those measurements. And what they did is they had one system that measured at 1 meter above the ground and one system at 2 meters, right? So it's not too far from each other, but already from those two sensors, you already see the differences in the sin square, meaning that the turbulence is stronger, the closer to the ground, the stronger the turbulence, basically, right? Which we can understand because, the sun is hitting the ground and the gradient in the temperature and the atmosphere are larger the closer to the ground. So the turbulence itself is stronger when you are close to the ground, and when you move above, just 1 meter above, you already see differences. So typically in such type of image, there's no reason that so here, those are simulations, so we know it's the same blur, but on real images, there's no reason that the blur will be with the same strength when you are on the bottom of the image compared to the top of the image. And so that's something that we are also thinking of, is instead of having one kernel that will be used for the whole image, we might also have a spatially dependent kernel. But it complicates things quite a little bit.
Yeah.
But that's something, that's something to think of. Yeah, definitely.
Okay. Thanks.
A quick follow-up on the previous question, if I may.
Sure.
Going opposite to your answer, Jerome, on the previous question, what about if you assume that the kernel is isotropic? At least most of the images and results you have showed us, the resulting kernels are extremely isotropic. So if you do assume that they're isotropic, wouldn't your code will run much faster? You're trying to reconstruct a one-dimensional object instead of a two-dimensional object.
I'm not sure to follow you. What do you want to do? Can you speak a bit louder?
Yeah, so if instead of assuming, not assuming anything about the kernel, you do assume that the kernel is isotropic, the reconstruction is just a 1D reconstruction instead of a 2D reconstruction. That means that it will be much easier to reconstruct much faster. And all the images you have showed us, the kernels tend up to be extremely isotropic. So I don't think you gain too much by requesting a 2D reconstruction. A 1D will be enough.
Wait. Are you saying that we can perform a 1D deconvolution on the image with respect to a particular direction? Is that what you're saying?
I'm saying that the kernels that you're showing up on the screen are really 1D because the radial part is the only thing that matters. Yeah.
Those are isotropic kernels. So it's like you are dealing with a 1D kernel. It's just a 1D kernel that you just rotate basically. So yeah, the parameters correspond to a 1D kernel. Yeah.
So you did not reconstruct the angular part of the kernel. You are just showing it that way for presentation purposes, but they are really 1D kernels, radial 1D kernels.
No, we actually build the kernel into the, for the algorithm, it needs the kernel as a matrix in the algorithm.
So that's precisely the point. You don't need to reconstruct a 2D kernel because it's isotropic. You only need to reconstruct a 1D kernel.
Well, numerically speaking, sometimes it's faster to actually build a 2D kernel than doing tricks to just be able to handle a 1D kernel. So now in terms of memory consumption, I agree that we use more memory, but honestly, the size of one image is nothing today. So we don't really care about that.
Okay.
Okay, on that note, we thank you, our speaker, Jerome. Thank you for a
Thank
very
you.
interesting talk. And
Yeah, first time giving a talk online.
well,
The
you
toast
got a
John.
chance.